starting the lecture, but this is a little lecture on memories. There are many types of memories, bad memories, good memories, but we are talking about uh, memory types. RAM, ROM. RAM has two types. One is called dynamic RAM, and this one has uh, static RAM. ROM has many types. Double E, ROM. This is electrically erasable read-only memory. And we have UV-ROM. UV-ROM is based on it is also erasable read-only memory, but you need to use a special eraser to erase the memories. UV-ROM. And then OPP, which is the one-time programmable ROM that is only programmed once. And it cannot be programmed again or reprogrammed again, one-time programmable. This type of ROM is used in like kids' toys or things like that, where you don't want to rewrite any ROM. So once there is a mass production, you can load your final data and it's never to be touched again. UV-ROM is used in often used to be used in computers in old days, and it had a window whereby you could program your ROM. So you needed a special programmer. Let me see if I can find one. UV-ROM देना programmer भी और eraser भी दिखाना यार. All right, so इसके so this is the eraser, UV eraser. You can put your ROMs here, and when you turn on, you can set the time, and when you turn it on, UV lamp is there and inside this. So that UV lamp strikes these ROMs, and these ROMs are get erased. So as you can see here, there is a small little window in each IC. Inside that window, there is a chip, that is exposed to UV light, and it helps erasing the whole of the memory. So that's the role of the UV ROM eraser. And this is the ROM. Once you have erased your program, you need to program it particular data again. So you use this kind of programmer to put your ROM here. You put your program here in ROM in here. So it gets fixed inside. Once it is fixed, you can then program it using this USB cable. So once it is programmed, you cover this window with the black tape. So once it is programmed, you can cover this with the black tape. So this is a special ROM program. Once you cover it with the black tape, then the data stays for 20 years. So whatever is the data stored in here, it is like flash. It stays there for 20 years. It's not, 1,000 year storage. It is not. It is for 20 years. Also, it has a particular number of arrays and store cycles. You can't really uh, infinite number of arrays and stores cannot be done on this UV ROM. So this is the and tomorrow's lab will be using UV ROM to test our some particular uses of UV ROM. Very, very powerful thing. Very, very powerful. This UV ROM is one of the most interesting thing for the hobbyists because they can do so many projects using UV ROM. All right. So here, Flash is like the electrically erasable read-only memory, but this technology has been, proprietary technology. It was much faster. However, all the other characteristic of ROM still remain that you can only rewrite it a number of times, and the data cannot stay forever. After some time, data will be lost. After 20 years time, there will be no data. Uh, uh, retention is only limited. So just like any USB, once you have written your data in USB, it stays there. No power needed. That's the interesting part about this UV ROM also. Once you have written data in there, you no power needed. And in the old days, uh, uh, इसमें नहीं है ना यूवी राम लगी जिसमें नहीं है. Okay, so dynamic RAM is basically static RAM is made out of D flip-flops, and that we have already studied. So this RAM, static RAM, is made basically D flip-flops, or you can say D latch or SR latch. So this is just 2 NAND gates are needed to make a static 1 bit storage in a static RAM. A dynamic RAM, on the other hand, requires the capacitor to store a charge, and The charge, a capacitor that is charged is said to have a stored value 1, and that is not charged is thought to have stored value 0. And since capacitors lose charge over time, they need to be refilled, updated, what we really say in this word of DRAM, they are called, you need to refresh uh, data. So when the RAM is not being used by the computer, there is a refresh hardware that takes over the RAM, and it reads the data from a particular ration, particular value, and rewrites it on the same location. So by rewriting the data on the same location, it basically refreshes that all the capacitors again. So that way, uh, you have a dynamic RAM to store different types of data. And if the refreshed circuitries were not there, this data wouldn't stay for more than few milliseconds. And static RAM, there is no refresh circuit because they are NAND flip-flop. The advantage over here is that the density, you can have very big dynamic RAM, DRAM, uh, like 8 gigabyte or 16 gigabyte DDR double data rate dynamic RAM. Static RAM, on the other hand, has flip-flops, so the density is much less than the dynamic RAM. And the static RAMs are used for cache. So the cache level 1, 2, 3 are they? These are the memory technology that are used in caches. Caches have very much high speed, and but they have high density, low density also. So the cost of the silicon, what they call is real estate, in sometimes it's called real estate, is very high with static RAM compared to dynamic RAM. Dynamic RAM, you can fit lots of RAM on small amount of uh, real estate. So what is basically why RAM is called a RAM? Often I ask people why a RAM is called a RAM. To understand that random access memory. Uh, so of course there are no students here. So to whom I can ask why they are called RAM, why RAM is called a RAM. So uh, in fee center terminology, RAM is something that in the desktop, that's where uh, temporary data storage is done in RAM. But what actually the word RAM came from? And you will notice that by that definition, ROM is also RAM. So where that definition came from? Uh, hello?
हेलो ये सर
आवाज आ रही है ना?
जी सर
Mhm. So by definition, where does what is RAM? Basically, RAM has a very simple symbol. All memories have a very simple model. This is RAM or ROM, whatever you can say, ROM slash RAM. Model is very simple. Or that this symbolic representation of ROM or slash RAM is very simple. Uh, you write the ROM or RAM, whatever it is, and here it is mentioned the size. Size of RAM is 2 raised power n multiplied by m, where n is basically uh, 2 raised power n is total number of locations. and m is 2 raised power n, and m is data stored at each location. Data stored at each location. So if the memory has 64K multiplied by 8, that means there are 64K. And these 64 is K in case of ROM or RAM. This 64K is nearest value to 2 raised power something. So 64K is nearest to 2 raised power 16 multiplied by 8. So that means it has roughly 64 kilobytes of 64,000 locations, and each location is has a data storage capacity of 1 byte. So 64K is basically 2 raised power 16, which is actually equal to 65536 multiplied by 8. So this is the 2 raised power 16. So you can see that there is a difference between 64K. So for memories, only for memories, this terminology is used. So sometimes it is also called, this memory will be called 64 uh, kilobyte. KIB in modern terminology is called 64 kilobit. Megabyte is MIB, gigabyte is GIB. So KI means 2 raised power something. So it's not really 64. So this is exactly the total number of locations inside this RAM. So multiply by 8 means 64K multiply by 8 means you have a 8-bit data bus. 8-bit data bus. And 64K. So 64 is K is 2 raised power 16. So that remember 2 raised power 16 is N. So N is equal to 16, which is the size of the address bus. ठीक है आवाज आ रही है ना अभी भी साथ
Yes, sir, are you?
So this is the address bus. There are 16 lines of address bus. If I pick up a ROM data sheets with this size, you will see that there are pins over here which go from A0 to A15. And there are data lines which go from D0 to D7. And the model is very simple. In case of ROM, it is even simpler. Once you have written your data onto ROM, you give any address over here uh, using logic switches or whatever. When you give an address over here, you will have 8-bit data at that memory location. It will appear over here. So since there are 16 switches, you can do 2 raised power 16 different pointers or addresses you can generate. And each location will give you 8-bit data at the output. So in case of RAM, you also have two more signals that are associated with this. One is, of course, enable, and other one is very important, and that is read write. Read write. So since there are only two operations allowed on RAM. One is called a read operation. In this read operation, you give a address on this pointer or address bus. Then you do enable, and then you wait, because this is not a zero time device. RAM is takes time. Wait. Where do you find this wait time? This is given in data sheets. When you install a RAM or a ROM inside your computer, RAM install करते हैं, तो कंप्यूटर के अंदर एक स्मॉल लिटिल हार्डवेयर मदरबोर्ड पे होती है, जो कि इट फाइंड्स आउट के ये जो मेमोरी लगी है, इसका कितना वेट टाइम कितना है, कितनी देर वेट करेंगे. तो वंस यू गिव एन एड्रेस, it takes time to give you the data. So after wait, what happens is that the data is ready. To read. If you cannot read it before this wait time. In case of write operation, you give an address. All right. So enable के साथ you must also activate read write equal to 1, because 1 means read. So 2 will be data that you want to input, because in write operation data is provided by the user and it travels in this direction and it is written onto the memory. So the data must be over here in case of RAM. So data is input over here, address is given over here. So now it memory is ready to given the third thing, and that is enable. And then you can say read write equal to 0. So then you wait, but of course, once you make read write equal to 0, this address on this address, this data is written. So processor does that in steps. Address is given the first thing because it takes long time to find out which location is to be written to. So basically, address is the pointer which points to hundreds of 65,000 locations in this memory. So the bigger is the memory, bigger is the address bus, and bigger number of location is also big. Total number of locations are 2 raised power the address bus. So using this concept, you give data, and this is the sequence of operation that you need to do when you want to use RAM or ROM, RAM, sorry. So coming back to the question, what is random access memory? So what is random access memory? And by this definition also can be applied to ROM. भाई साहब आपको पता है क्यों कहते हैं रैंडम एक्सेस?
नहीं सर.
Random access basically means that no matter what address you apply here, no matter what address you apply, the wait time will be same for the data to appear at the output. ये नहीं है कि आपने 000 एड्रेस दिया है तो ज्यादा टाइम लगेगा, कोई और एड्रेस दिया है तो कम टाइम लगेगा. कोई डिस्टिंक्शन नहीं है. Randomly you can give any address to the address bus and the data will be written. It was basically called random access memory because before that there was tape drives on which data was written, and tape drives were sequential circuits, like a little bit like hard disk, where you have to move your tape head to particular location before you could write your data. And moving that tape head like a tape recorder would take uh, mm, you know different amount of time, non-equal amount of time, depending के और टेप में कितनी जगह खाली है और कहाँ पे आपने डेटा राइट करना. It's like reading songs from an old tape. शुरू के सॉन्ग जल्दी प्ले कर सकते थे, एंड के सॉन्ग्स के लिए आपको पहले उसको फॉरवर्ड करना पड़ता था, एंड दैट डिपेंडेड ऑन के कितनी देर के लिए उसको फॉरवर्ड करना है. देन यू कुड प्ले द लास्ट you know some other song. So that was sequential storage. In the beginning that was sequential storage. Then came ROM, and the name came from there. Then random access memory means you give any address over here, any address, and data will be ready. ये कोई भी खाना आपने पकाना है, कोई किसी किस्म का कोई भी खाना आपने पकाना है, एक सर्टेन टाइम लगेगा, उसके बाद खाना तैयार हो जाए. ये नहीं है कि एक खाने को जल्दी दे देगा, दूसरे खाने को देर से पका के देगा, ऐसा नहीं है. So all access memory accesses have equal time. So basically randomly access memory with equal time इसका नाम होना चाहिए था, randomly access memory with equal time. ROM by that definition is also random access, because in case of ROM also you can give any random address over here, and after a certain wait time which is constant for a particular RAM, for example a 70 nanosecond RAM, you have to wait 70 nanoseconds before the data will be available at the output. So you can find out these in the data sheets कि कितनी देर बाद data output पे available होता है. कंप्यूटर में जब आप लगाते हैं मेमोरी तो कंप्यूटर खुद ही पहले जमाने में बताना पड़ता था कि एक जमाना था व्हेन यू हैड टू गो इनटू बायोस एंड सेट द एक्सेस टाइम ऑफ द रैम, बट नाउअडेज दे हैव plug and play, everything is plug and play. So you just plug your RAM and small little firmware runs in on the back and it finds out what is the access time of the memory, and processor adjusts its memory access rate according to that time. So one access time could be 70 nanosecond, for example. then the memory access rate will be at least 1/70 nanosecond. These are number of data accesses you can make from this. So 70 is access time for any location you read from this. क्यों भाई अब समझ आ गए साथ कि रैंडम एक्सेस का क्या मतलब है?
यस सर, अब आ गया।
हाँ, कोई भी डाटा रैंडमली आप डैश दे दें, कोई भी प्रोसेसर इज गिविंग डाटा एट वेरी हाई स्पीड, बट इट हैज टू वेट एनी डाटा। पॉइंटर के साथ कोई नहीं लिखा होता कि इस पॉइंटर को इतना टाइम लगेगा मेमोरी से रीड करने के लिए। ऑल पॉइंटर्स आर सेम। So a read operation is sometimes also called a load operation, and a write operation is also called sometimes called store operation. So load and store. Okay, so that's the basic idea of ROM. Uh, the question is, how do we make a ROM? So we'll talk about static RAM. Basic RAM cell can be any, but let's talk about static RAM. How do we make a RAM? So what you have is in a stack. Let's design 8x1 static RAM. So basically 8x1 static RAM means you have 8 locations and each location has a 1-bit storage. So one basic component that is needed in ROM, that I think is the point I was waiting for a long time to teach this component. But one basic component that is needed in ROM is a tri-state buffer. So what is a tri-state buffer? It's a very interesting device, very interesting device. Our tri-state buffer is, this is a symbol of a tri-state buffer. Now, basically, buffer means that you give 0, output is 0, that is the buffer. Simple buffer. Simple buffer would be that you give 0, output is 0, give 1, output is 1. So what is the use of a buffer if this is the state? क्या use हो सकता है buffer का? The use is that sometimes you have a device that you want to directly connect to the to like an LED. a very high power LED. So buffer has zero input, zero output. When it has one input, it will have one output. But the current capability of this buffer, normal IC maybe only can give you 20 milliampere, but this may give up to hundreds of milliampere. So when that happens, this is enough to switch on the LED or a bulb. So normal will be normal like this, normally, maybe even less, 20 milliampere, less than. But with the buffer, the current capability is very high. So at 5 volt, it apply it at 5 volt, it gives you 20 milliampere, which is if you calculate that, that is equal to 100 milliwatt volt into current. But with the buffer, it could be 100 milliampere. So uh, buffer could have greater than 100 milliampere. So that case, 100 milliampere at 5 volt will be equal to 500 milliwatt, yani 0.5 volt, which is quite a lot to run a small little device. Normal device like normal IC, TTL IC has less than 20 milliampere, which is less than 0.1 watt. So basically, a buffer has larger power power capability. It doesn't do anything with the digital data. 0 means 0, 1 means 1, or 5 volt means 5 volt, 0 volt means 0 volt, but it has higher current driving capability. So many LED, many buffers have direct LED connections that you can make with them, so that you don't have to have a separate LED drivers to drive. So some ICs come with direct buffer at the output, so that you don't have to use special circuit for LED driving. Or you can use a relay also to directly turn on a relay or something like that. So that's the job of the driver uh, buffer. A tri-state buffer has a third state. A tri-state buffer has a third state, and that is enable. When enable is one, it acts like a simple buffer. But when enable is zero, what happens? When enable is zero, what happens? When enable is zero, is this output is said to be in high state, high impedance state. Now this is the third logic signal. Fourth logic symbol that we have introduced. One was don't care, one was 0, 1, and this is another one, which is Z. Z means high impedance. So basically, what is high impedance? This thing over here, what is high impedance? High impedance. High impedance means that this circuit goes into very high impedance state, means no current can flow in this direction, no current can flow in this direction. Basically, you can say that this connection is totally broken. There is no connection here. You can imagine like this. There is no connection here. If I give you an example, Say I have this wire with me. So if I connect one end of this wire to 0 volt, I will get 0 volt over here. So if I connect this wire, this is the other end of the wire. If I connect this wire to this ground side, I get 0 volt. If I connect this wire to this side, I get 5 volt. What happens if I connect this wire to nothing? This wire is open like this, is not connected to anything. What will be the voltage over here? So we say the output is floating. In electrical engineering, साद आप डबल के हैं या सी एस के हैं?
Sir, double E.
Double A. So in electrical engineering, it's called floating output. Means it's not, it is ready to be connected to anything. If I connect this to this, it will be 0 volt. If I connect to this, it will be 5 volt. So if I have meter here and I connect to meter से इसको measure करूंगा, अगर 0 से connect है तो मीटर मुझे 0 volt देगा, अगर 5 से connect है तो 5 दे देगा, अगर दोनों से नहीं connected तो मीटर मुझे क्या देगा? हम कहते हैं कि 0 देगा, लेकिन ऐसे नहीं है. 0 नहीं, कोई नॉइज पकड़ लेगा हवा में से, और मे बी अगर आपका बहुत ही सेंसिटिव मीटर है तो आपको मिली वोल्ट, माइक्रो वोल्ट इस तरह से वेरिएशन आ रही होंगी, बिकॉज इट्स नॉट कनेक्टेड हियर, इज नॉट कनेक्टेड, so it will be open circuit. And this has a huge role in memory circuits, even in communication, in computer to computer communication, like Ethernet and many other communication protocols. This floating output has a big role. So what is the usage of this? Usage is this, that you have this, and you have this over here, this. This is enable 1, this is enable 2. थोड़ा नीचे कर लूं. So this is enable 1, this is enable 2, this is input 1, this is input 2. Now what I can go is, usually you will notice that we have never done this, that we can short the circuit these outputs. Tri-state buffer, you can do that. With that, there comes a huge responsibility also. When you do that, it's not a small game now. So what you do is that if you make a truth table for this circuit, you have enable 1, enable 2, you have in 1, you have in 2, and you have this output P, a bus line, a party line, whatever you can call this. So when this is 0, enable 1 is 0, enable 2 is 0, this is don't care, this is don't care. These two are open circuit like this, wiring is connected. We say that the output is high impedance state. Floating, output is floating. When this is 0, this is 1, like a multiplexer, exactly like a multiplexer. When this is 0, this is 1. In enable 2, in 2 will appear over here, into into जो भी है 0 1 है, तो ये 0 1 हो जाएगा. अगर यहाँ पे मैं लिख देता हूँ, चले 0 1 0 1 depends on into, you don't care. When this is 1, this is 0. In 1 and in 2 is don't care. If this is 1 0, this is 1, this is 0 1, and this is in 1. So what happens if you make both of them 1? That is the danger. When you make both of them on, because when it is on, it has almost zero resistance. Zero resistance. When this is off, it has infinity resistance almost, just like a switch. When it is on, uh, say for example, if it is on and these inputs are conflicting inputs, this is also 1, this is also 1, 0, then the huge amount of current will flow through this. तो यूजुअली इसमें वो टेक्स्ट बुक में यहाँ पर उन्होंने वो जलने का निशान लगाया होता है कि जी सड़ जाएंगे दोनों, तो डोंट डू दिस. स्मोक, स्मोक कैसे बनाए? ये फायर है, बारबेक्यू फायर, तो यू गेट अ स्मोक. बेसिकली आईसी, कोई ना कोई आईसी सड़ जाएगा. So you don't make both of them enabled at the same time. And if these are अब यहाँ पे भी हाई स्पीड डाटा आ रहा है, यहाँ पे भी हाई स्पीड डाटा आ रहा है, तो we say that data has collided. So this is when you say that data collision can occur. Data collision. This data will collide with this data, and the resultant data will be not be readable. So package drop हो जाएंगे सारे के सारे. So this is a very important uh, way of connecting different outputs together on one single line. And this is called the use of the tri-state buffer. So very important tri-state buffer. So coming back to the memory IC here, this is shown as a symbol over here. This symbol means that when enable is 0, this enable is 0, data bus is floating. It's like this IC is not present in the circuit. Total IC निकाल के बाहर रख दिया आपने. It's not present in the circuit. So this is very powerful combination. क्योंकि डाटा बस पूरे कंप्यूटर में हजारों जगह जाती है. तो जिस चीज के साथ प्रोसेसर ने कम्युनिकेट करना होता है, उसका एनेबल 1 कर देता है और उसकी डाटा बस उसी डिवाइस से कनेक्ट हो जाती है. So in a rough way, I can say something like this. So basically, this is processor. So processor also has a data bus. And there are many peripheral devices or memories connected to this. So this could be RAM that is connected to this bus. I'm not showing that that's bus. That's bus भी होती है, मैं अभी वो show नहीं कर रहा. This could be a ROM. This could be connected to this data bus. This is processor's data bus. This could be some peripheral device like a graphics card, network card. This could be connected with this data bus. But all of these outputs are tri-stated. All of the outputs are tri-stated. Address bus is going to all of them. So basically, address bus is going to all of them. I can show it like this, that ये address bus जा रही है, address bus is going to all of them. प्रोसेसर जो है ना इज मास्टर ऑफ द डेस्क बस. इसको पता है कि रोम किस डेस्क पे है, रैम किस डेस्क पे है, नेटवर्क कार्ड किस डेस्क पे है. सो इट इज द मेन मैनेजर ऑफ द डेस्क बस इन एब्सेंस ऑफ पीसीआई. पीसीआई के बाद तो खैर थोड़ा सीन चेंज हो गया, बट आई एम टेलिंग यू द ओल्ड थिंग. So this is actually the responsible address bus. CPU is in charge. It knows where the data is, and it generates the pointers for different memories, RAM and ROM. And it also has some enables also. मैं अभी तो फिलहाल इस तरह ही शो कर रहा हूँ. Later on, maybe if I have time, I will show you कि actually ये enable किस तरह बनते हैं. But let me just show it in these enables like this. It has plenty. You can make plenty of enables, and each enable controls. जब ये वाला ROM enable होती है, ये दोनों disable हो जाते हैं. तो प्रोसेसर को यूं लगता है जैसे ये इनको एड्रेस जा रहा है, लेकिन डाटा कोई नहीं ये कनेक्ट होता. ना डाटा इधर से इधर जा सकता है, ना डाटा इधर से इधर जा सकता है, बिकॉज दीज आर टोटली प्रैक्टिकली कट ऑफ. When you are talking to RAM, ROM is cut off, network card is cut off. When you're talking to network card, ROM is cut off, RAM is cut off. अगर डाटा उसने नेटवर्क कार्ड से लेके रोम में एंटर करना है, तो पहले वो नेटवर्क कार्ड से रीड करेगा सीपीयू किसी रजिस्टर में. उसके बाद वो इसको एनेबल करेगा रैम को, और वो से रजिस्टर से तो डाटा इधर जाएगा. सो फर्स्ट इट विल रीड द डाटा फ्रॉम द नेटवर्क कार्ड by giving an address in the memory space where the network card is addressed. कौन सा पॉइंटर है जो कि नेटवर्क कार्ड को एड्रेस कर सकता है. So by giving that address, it accesses the network card. So the data from the network card will come here. एक byte of packet, maybe 1 byte of packet, and this packet will then go to the memory over here. डेटा बस अगर 8 बिट की है तो 8 बिट का डाटा जाएगा, अगर 64 बिट की है तो 64 का बिट का डाटा जा सकता है, अगर 32 बिट की है तो 32 बिट का डाटा एक ट्रांजैक्शन में चला जाएगा. So these tri-state buffers are basically, they can switch off things, switch on things, just like as if they are not there. Basically, they are simple transistors like this. Enable. When this is enabled, is 0. This transistor connections are at very high impedance. When enable is 1, is short circuit. Current can flow from here to here or here to here. In CMOS transistor, current can flow in both directions, no problem. So this is basically the circuit. Just one transistor is needed to make a tri-state buffer. So when this transistor is off, as if it is not there. Very high impedance. Very, very small. In case of CMOS, if you remember, CMOS has very, very low leakage current. So draws very low leakage current when it is cut off from this bus. The processor has this data bus going to so many devices on the motherboard, and by using this technique of a tri-state buffer, it can communicate to any bus at any time. So that's the idea of tri-state buffers. So we were talking about how to make 8x1 storage. So for that, inside an IC, inside one memory, usually there is no tri-state buffer. Internally, there is all that is all of it is basically uh, made up of gates. Book shows with an RS flip flop, but if you remember an RS flip flop with the inverter over here is nothing but a D flip flop. बुक ने डी फ्लिप फ्लॉप आरएस फ्लिप फ्लॉप ड्रॉ किए और यहाँ पे कहीं एक इन्वर्टर लगा दिया दोनों के बीच में so that doesn't make sense so I will going to stick with the D flip flop. So these are D flip flops. 8 of these flip flop will be needed. Each such D flip flop थोड़ा छोटा कर देता हूँ so that I can make more of these. 8 of these D flip flops. So the D input is going to all of them. Why? Because 8-bit storage, 8x1 RAM will have uh, how many locations? 8. So it will have 3 address lines, A0, A1, A2. And it will have just one data line, D0. So this is 8x1 RAM. इसको sometimes it is called a RAM slice model. So this is a one RAM slice, 1 bit of data. So all of the data input is going there. So this is also D flip flop. So there are all locations that you can write. This is the data input. Inside this RAM, we can say that input data is coming here and data output is over here. So within this location, inside the location, these are two divided like this, that we have one flip flop like this, one tri-state buffer like this, one tri-state buffer like this. You enable this tri-state buffer, data can come and go in this direction. So this will be when you are reading data from this line. This is the line from you. When you enable this, then the data is go from this to in this direction. So this is a when is this enabled? When data goes into the memory. When data goes into the memory is the time when you are writing data to the memory. So this is enabled when you are writing. And this is enabled when you are reading. The data is going from data memory to the external wire. So this is how you convert this bidirectional line to two different lines. One is input data line, one is output data line. When this is enabled, this is not enabled. When this is enabled, this is not enabled. So ये नहीं हो सकता कि ये डाटा इस तरह से सफर करके वापस चला जाए. When this is enabled, data can read, come from the memory and go in this direction. When this is enabled, outside word से data आता है and in इससे memory को चला जाता है. So that is the read cycle, and this is how this bidirectional dash line is converted to this line. This is bidirection, this is, and this circuit is used inside this. Buffers are everywhere. These buffers are, tri-state buffers are everywhere. So we have this data line, data in over here that you want to write into any of these memory locations. But you have to choose one of these memory locations. So आपको याद होगा कि to have one of these memory locations, you need a decoder. So decoder will have three address inputs, which are the address lines A0, A1, A2. अब ये जो decoder है, this decoder has output going to the clock. This decoder output is going to the clock. So when you make an enable output high, at that time, this decoder output, one of the decoder output becomes one, and that generates a clock on one of these D flip flop, and that data is written only onto that D flip flop. So you say that we have written one data. You want to write into this or this or this, any you can use to write a data here. How to read now? The question is, how do we read? So read is this that for read purpose, we use this circuit, enable circuit, like this. Here we have an AND gate. Now, and all of these outputs are odd together. Now to show all of them are, we sometimes use this symbol here. When we have many inputs to an OR gate, वो हम कभी कभी ये वाला सिंबल भी शो कर सकते हैं, ये वाला. This means that there are many wires coming in to the OR gate. Wire, this wire, they are going to this OR gate, and the output of this is basically OR. So this is called और गेट। ये मछली का स्केल्टन की तरह का और गेट है। इस तरह से आप इसको इस तरह से शो भी कर सकते हैं, मछली के स्केल्टन की तरह का और गेट। सो ऑल ऑफ दीज आउटपुट्स आर वायर्ड और की होती है आपस में। As you can see here, normally this enable signal is zero, so it is in the read mode. So any address is forever, whatever is random address over here, it is giving the data output. But outside this, and similarly, it can, when you only want to write this, you can write data into one of these T flip-flops. So that way it works like that. You can read and you can write. So this is the 8x1 memory with 8 locations. This is the location 000, location 001. So this memory has a pointer size of 3 values, 3 addresses. So any memory location can be written to or read from. So I think I'll end our lecture here today. Thank you very much, and see you on hopefully on Wednesday. Allah Hafiz.